have a graph having 4 nodes only A, B, C, D, and 4 number of edges. In this case, we have directed graph. So it means that we have an edge from B to C, but we don't have an edge from C back to B. It means that we can only travel one directional for this edge. But we have an edge from A to C and another edge from C to A. In this case, we have a circle here, and we can travel in between these 2 nodes, and another edge from A to D. Now, transitive closure, as we discussed in the subject, saying that a transitive closure tells us that whether we can go from any node to any other node through a path. For example, from the adjacency matrix here, we are not immediately clear that whether we can go from B to node D. But from the graph itself, we can see that we do have a path from B to D, because we can go maybe B to C, C to A to C, C to A, and then A to D. Right? This is just one possible path from B to D. But from the adjacency matrix itself, we are not sure if it's possible. So the transitive closure is a graph that can be generated from the original graph. And the edges are generated such that if from the original graph, we have a path from I to any node to J, this question mark means that we can find a path from I to J. It could be I to J directly. It could be I to a stepping stone, then to J. It could be I to 2 stepping stones to J, and so on. As long as we can find a valid path from I to J, then we're going to have that edge in the transitive closure. One way of drawing the transitive closure, one way of generating the transitive closure of a graph would be, we can start from each node, then apply DFS or BFS from that node to see if we are starting from that node, which other nodes can we reach? And we can repeat this for each of the nodes. And another approach we can consider is the washout algorithm that we had in the lecture. Let's consider the washout algorithm here. So how the washout algorithm works? So we have the original graph. Let me quickly copy and paste this matrix here. 0, 0, 1, 1, 0, 0, 1, 0, 1, 0, 0, 0, 0, 0, 0, 0. So this is the original adjacency matrix of the graph. And what we're going to have is, we're going to consider in the first round, we are trying to check if it's possible that we can go from any node, then to A, then to J. And J is also any node. So we're using, in the first round, we're using node A as a stepping stone to see if we can go from I to A to J. If so, we're going to update I to J as 1. Now, if we look at the first row in this adjacency matrix, originally the first row tells us whether we can go from A to one of these A, B, C, D nodes. And if we are taking A as the stepping stone, what it means is that whether we can go from A to a destination node. And the question mark here could be A or B or C or D. And since from the matrix here, we can see that A to A, this is not possible at the moment. It's not possible yet. So in this case, by using node A as a stepping stone, we cannot go from A to any other node. So we will have no updates on the first row. Now, if we consider the second row original means that whether we can go from B to other nodes, A, B, C, D. And now in the second row here, we're going to consider whether we can go from B through our stepping stone to any other node. Again, we can see from the matrix that B to A is not possible yet. So again, we are having no updates. Now, if we consider the third row, we're checking whether we can go from C to A and then to a destination node. And looks like C to A is possible because from the original matrix, we have C to A possible. Now, this tells us that if we start from C and using A as a stepping stone, we should be able to reach any node that A is reachable. For example, we can go from C to A, then A to C, telling us that C to C is possible. We can also go from C to A, then A to D. That's also possible. So we know that C to D should also be possible. So I think in this case, we're going to have two updates. We're going to have these two zeros updated to 1. And for the last row, we are checking if we can go from D to A and then to a destination node. But since D to A is possible, we are not going to have any updates here. That's the first round we get. And for the second round, we are going to use the second node, node B, as a stepping stone. So we're checking if we can go from any starting point to B, then to the destination. And it looks like in this case, we can clearly see from the graph that B has no incoming edges. So it's impossible to have any node go through B as a stepping stone then to reach any other node, because there's no way we can go from anywhere to B. So this means that we cannot do any updates here. So W2 would be same as W1. And for W3, we're using C as a stepping stone. By using C as a stepping stone, I think we're going to have a few updates. For example, in the first row, we are checking if we can go from A to C and then to any other node. And since A to C is possible, as we can see from W2 or W1, A to C is possible. So it means that any node that C can reach should be reachable by A. And for the second row, since B to C is possible, it means that any node C can reach should also be reachable by B. And for the third row, we will have no updates because it's C to C and then to any other node. And the last row will not be updated because we cannot go from D to anywhere. I think that's it. And for the last round, we will have the last node D as a stepping stone. But since D does not have any outgoing edges, so we're not going to have any updates, even though we're going to check each of these 16 cells. Now the final matrix W4 would be the transitive closure of the original graph. And since W4 here is same as W3, we can just refer to this adjacent matrix. And this would be the transitive closure of the original graph. And we can clearly see from this that if we start from A or B or C, we should be able to find a path reach A or C or D. I think that's it for today. We'll have the Floyd algorithm covered next week as the first question in the tutorial, which is the same idea of the washout algorithm, but with tiny modification to it. We'll also have digester algorithm and print algorithm covered next week in the tutorial. Thanks for joining us, and I'll just quickly try to see if I missed any question from the chat window. Is big O log V plus E superior to big O log E or big O log V? I think this question is same as the previous one, whether OV plus E is superior to OE or OV. Log V plus E is strictly larger or equal to log E, and it is also larger or equal to log V. I think that makes sense because both V and E, they are positive integers if we are not considering zero, right? We can have a graph with zero number of edge, but let's just don't worry about it. And another question from the chat window, what if loop in A and C times at times? Do you mean that we stuck in the loop, stuck in the circle A to C, C to A to C, C to A? Yes. Well, you can find the path from B to D. That's the point. In the transitive closure, we are not actually traverse the graph. If we are trying to traverse the graph, we will find that we start from B maybe, and then we go B to C, C to A, and then A find another path coming to C, and then we may stuck here. But in transitive closure, we are not actually going through any of the paths. We're kind of using a dynamic programming approach here to find out whether we can use each of the nodes as a stepping stone to help us find out that node I can reach node J. And I think the thing that you are worried here, with if we are stuck in this circle, we're going to have this next week in the Floyd's algorithm. Well, that should be the first question next week. In Floyd's algorithm, we're going to consider if we have negative edge weight in the graph, then Floyd algorithm may not work because we can just repeatedly traverse through that circle over and over again. And we can never get a minimum total edge weight. And we'll also discuss next week about the requirement for applying Floyd's algorithm and also Dijkstra's algorithm. We should not have any edge having zero or negative edge weights. All right, thank you everyone. Enjoy the rest of your week, and I will see you next week.